That's just too sweet. Okay, so we're talking about the cell. What we've done so far is we've gone from atoms to molecules, we've bonded them together, and then we built them into really big macromolecules like your starches, big huge carbohydrates, and then we did proteins, which are at least 50 amino acids in length. We did nucleic acids like DNA and RNA. They're made out of nucleotides. And then we did those things called lipids that don't look anything like that. So once we know the four biological molecules, which are basically carbohydrates, proteins, nucleic acids, and lipids, okay, those are our four categories, we use that to build a cell. So, basically we're just trying to work our way into understanding what a cell is and how it works and how it produces energy. And for the most part, this entire semester is really we don't go much further than just one cell. That's it. So believe it or not, it seems like, there's so much information and it's such a short period of time. But we're not doing, in terms of biology, we're not covering that much information, although the information we're covering is critical. It is so critical. Because if you don't get a handle on this, I'm telling you, the rest of it isn't going to make a whole lot of sense to you. I'm not saying you can't pass without understanding it completely, but it will certainly be to your benefit to understand it. So you've got lots of help if you need it. We're certainly available. Okay, so we use light microscope, the compound light microscope. That's what we use in our lab. The highest magnification you're going to get out of that is 1,000. So, that one has the scanning lens, which is 4x. You've got the low power, which is 10x. You've got the high power, which is 40x, and then the highest magnification is actually called the oil immersion lens, and we've yet to use that. So we will probably use that. It's a good class. Sometimes the classes are not so good, and you're just like, no, you're not touching that lens. It's like, no, we're not breaking out the oil. You guys are good, so we'll break out the oil for you. Anyway, these are the two things that you have happening in the microscope. One is what is called a magnification. Actually, you're just increasing the size of that object compared to its normal size. So if it's on 4x, you've increased it 4 times, but of course if you're looking through the ocular, you've increased it another 10 times. So the total would be the 10 at the ocular and the 4 at the scanning lens. It's magnified 40 times. Your total magnification on low power would be the 10 at the ocular and the 10 at the low power, which is 10. 10 times 10 would give you 100, and so forth on that. Okay, so resolution. Resolution, yeah, if you want to text, you're welcome to leave. If you're not interested in listening, that's cool. I have no problem with it. But yeah, you're not going to text in here. So, I'll just tell you to leave the next time I see that. So, I understand. I do a lot of texting. I have a friend that was in surgery yesterday for 7 hours, brain surgery actually. And I got a text last night pretty late saying that she got out and she was doing fine. And so, believe me, I do texting as well. And, some things are very important, and I do understand that. So if you're taking care of real important business, I understand. I know what important business is all about. I really do. So it's cool, just go outside and text, and when you're done, come back. If you don't want to listen to me or learn anything about the class, take another class. Take someone else's class. You don't have to be in here. And I'm not jumping on you. I'm just saying in reality is, I don't want to spend my kind of time dealing with people who just absolutely are in here doing other things. That's not why we're here. So let's just do what we need to do and move on. We all know that we're We're crunched. We're crunched. Oh, man. All the students that I've had before that I've talked to on campus, it's like, what do you think about this 8 weeks? And they're like, oh, man, it's killing me. I'm going, yeah, me too. I'm killing, I'm dying. You know, I was up till, I don't know how late last night. Anyway. And I've got a cat at the vet, too, and they don't know what she has. And she's got a high fever, so you know, a friend having brain surgery and one of my babies at the vet. I am sorry, but it has not been a good week so far. This is just Tuesday. If it gets any worse, you know, I may come in crying. Don't be surprised. And my friend hadn't made it. I don't know how good of a shape I'd have been in today. Ugh. I'd probably been medicated legally. Legally, though, but just anyway. So that's magnification. You know, how much larger is this object than it would normally be? Is it 100 times larger, 400 times larger, or 1,000 times larger? Resolution is the ability to distinguish between 2 points that are very close together. And our microscopes are made by Nikon. The lenses are excellent. Nikon does not put out a bad lens at all. So if I had 2 lines that were very, very, very close together, you could easily distinguish those 2 lines. Excellent resolving power on these microscopes. So you get a very clear, sharp image, and that's really important because some microscopes are not like that. The ones we had before we got this were really just pitiful, I'm telling you. Luckily, we got grant monies, and we were able to get these, and we even have some cool stuff that y'all haven't seen. And we used to have a really, really cool scope, and it's called a dark field microscope. And I think I may have mentioned somehow it disappeared, and the nursing department had it. Of course, at the time, I think our department chair, and this has been many years ago, was dating one of the head of the nursing department, and then our dark field microscope left and ended up in nursing. I'm like, what? I used to like to break that out. It was a cool scope. I'll show you some images from a dark field microscope. Very cool. Anyway, so light microscopes, you know, we've been using it. We ended up with eventually what we call the cell theory. Now, originally, of course, they didn't have microscopes that they could just order. They had to, of course, make their own microscopes. And then in the 1800s, they developed a cell theory. Well, it's pretty simple. One is all living organisms are composed of cells. Hello. Sure. What else would they be composed of? Dirt? No. Cells? Yeah. If it's alive, it's composed of cells. And then the only way that you can get a cell is to have another cell. Now, believe it or not, you think, well, yeah, cells divide and you get more cells. That's pretty much common sense. That's how that works. But, you know, there used to be a theory called spontaneous generation, or actually, it was just a hypothesis, spontaneous generation, and they even had this formula, which is if I threw in this corner so many rice grains and so many rags and so many whatevers, then you could create a rat out of those things, which of course is ridiculous. But they did have that hypothesis. And then later on, people went, no, what? That's ridiculous. That doesn't happen. You know, only cells can produce other cells. It's the only way it works. So very simple. Now, the electron microscope, I'm not sure what year they developed this, but when I was in graduate school, actually undergraduate school, we had an electron microscope. And I never did get to play with it. I wasn't, you have to take a class in order to do that, and I never needed that class. And sometimes I look back on it and think, well, you know, even if I didn't need it, I should have taken it just to have gotten to mess with it, because they produce such an amazing image. The image magnifies up to 100,000 times, 100,000. Our compound light microscopes only go to 1,000. So 100,000 times, my goodness, you can see all kinds of detail, and they're wonderful. Here are the two types, scanning electron microscope. All you're doing is scanning the surface of the object. That's it. You're not going all the way through the object. You're not seeing through the middle of it. You're not seeing to the interior of the object, but you get some really amazing, incredible photos of the exterior of whatever you're looking at. And we'll show you some. And electron micrographs, which you will hear me say over and over again, that I'm just like, that person deserved an award. You know, why someone does not have an art gallery that just shows electron microscopy, you know. I mean, they have photography galleries, you know. I mean, not necessarily here, but in New York City they have them. And, you know, large metropolitan areas, you have areas that are big enough to where you have people would be very interested in that kind of thing. But, you know, if they had an art show with just electron micrographs in it, you know, I'd be like, I'm flying to Chicago. I've got to go see this, you know, would love to. Because I love these images, and I'll show you why. Now, transmission electron microscope, that means the electrons were to pass all the way through the object. So really, we're able to focus anywhere through. So you can focus just under, or a little bit deeper within the object, or a little bit deeper, and so forth. So you can focus all the way through and take photographs of these things, which then you can tell exactly what is inside that object, you know, which is super excellent. Scanning, you're just getting the surface. Transmission, you're actually focusing anywhere within that object. So this is a compound light microscope, although this one has a little bit more detail than what we can get out of ours, so that's a really nice one. Now, here's a scanning electron micrograph. So we're only getting the surface of the object. This is a paramecium. It kind of looks like a slipper. You could, like, you know, put your foot in and it'd be all nice and furry and soft, and you could wear it around in winter and just be nice and cozy. Start a fire and make some hot chocolate, or a bourbon and a little bit of honey and a little bit of lemon juice. Yeah, called a hot toddy. Not bad after you've had 12 of them. 12. Well, okay. Maybe not that many. But scanning, I think they're beautiful. I think that's absolutely amazing. I love it. Now, here's a transmission. You're going all the way through the, now this is also a paramecium, but you're seeing to the interior of that, so you're actually looking at the internal structures, which is very cool. This is dark field microscopy right here, and they didn't talk about it, but I love it. And like I said, we used to have one of those microscopes at the time, which was, gosh, you know, before you were born probably. Those were running like a $5,000. Who knows? They'd be 20 grand a day. You know how things are. You know, I remember being able to buy an automobile. You've heard these stories for $2,000. Gasoline was 19 cents a gallon. You know, blah blah. But, you know, cigarettes, you like a quarter. Yeah. Anyway, been a while. Been a while on that. Okay, so these things look huge, but cells are typically tiny, very, very small. And, you know, when we can get up to cells, the smallest bacterium, they're showing at about 100 nanometers. Now, what has me really frightened? Well, anyway, those are. Let me back up there. That would be I won't go into the other, but that has to do with the smallest of bacteria. Most of them will be like 2 micrometers in diameter, say like the size of a mitochondrion. And your viruses, notice how tiny those are, incredibly small. You're not going to be able to see that on a compound light microscope, we can't look at a virus. It's not going to happen. We can look at some bacteria, but the ones that are bigger, like 2 micrometers. And then, when you're dealing with plant cells are on the average about 35 micrometers. This is just an average number. There are certainly smaller and larger plant cells. Animal cells, on the average, we're looking at 10 micrometers. So obviously we can see those. And then we get up to the paramecium, which is pretty big. Human egg, notice that. That's over 100 micrometers there. Chicken egg is really one cell. The largest cell on the planet, ostrich egg. It is one cell. That's what it is. If it's not fertilized. And of course, you can get birds that lay eggs that are not fertilized. It is possible. They do it all the time. In fact, most of the eggs that you might buy in the grocery store are not going to be fertilized. And it's kind of weird to get one that has been fertilized. If you buy eggs from just an individual like my friend who just got out of the operating room last night, she raises chickens and she collects her own eggs. Well, she has a rooster. Well, the rooster sometimes fertilizes the chickens. And therefore, when she gets eggs and you crack them open, to make whatever, an omelet or some burrito or something, there's a chicken that'll fall out. Not fully developed, but it's just a chicken in the skillet. It's like, whoa, wait, let's scrape that up. I'm not eating this partially developed chicken. So, yeah, we can get chickens to lay eggs. In fact, they treat chickens anymore with so much estrogen. Chickens are females. So they treat them with so much estrogen that from the hatching, when they hatch, to when they start producing eggs, takes 21 days. 21 days from hatching, from being born to full sexual maturation, 21 days. That's crazy. That's how much estrogen they're putting on those chickens, which is why, and they give them all kinds of hormones, which is why, and I've mentioned this before, you get a Bush's chicken and you get a chicken breast that's this big. That's not a normal chicken breast, folks. Chicken, so you can imagine 2 of those. This chicken was like this. Looked more like a turkey. Not normal. And they used to treat, and they still do, pigs. So, you get these humongous pigs so that when they take them to market, they get a lot of money for them because they got lots of meat on them. Well, we get the fetal pigs, so we do dissection in the second semester, and you've got like arteries and veins that are growing. And normally you might have one subclavian artery that would be up here in the shoulder region, and that's where it used to start. And I've seen fetal pigs that would have 3, 4, 5 subclavian arteries growing in their shoulders, which is like, what? It's only supposed to be 1. Pardon? They give them too many growth hormones and, sex hormones. I'm sure cows, sure. And we're drinking the milk, and, it's a wonder we're not all 12 feet tall and sexually, mature at age 4. Oh, you're hot, baby. Let me get the diaper off. We'll get on this, Oh, whoa. Who knows? And so you've got 12-year-olds that look like, they're 21. You know what I'm saying? They're out there. Goodness, these junior high school kids. I'm just like, whoa, crazy. Anyway, that's why it's really good to eat all organic and very, very good to do that. And I try to do that whenever possible, for sure. Anyway, so human height, they've got this person at about, 5 meters. What would that be, about 15 feet tall? I always love that. He's a basketball player. Certainly, absolutely. Okay, so cell size, I do want to spend some time on this, talking about why cells are very, very small. It is, I believe, one of your discussion questions. And some people on Module 2 are having problems answering discussion questions. If you go to the far left, there's a bar, and it says Discussions. If you click on that, then you can go into cell size and then create a thread. So it's on, if you click on the cell size, some people are not able to get into it. I can, even if I put it in student view, and it's really weird. Because I dealt with the Blackboard person on that. With the last set of discussion questions that we had, she was like, and she even had to talk to the Blackboard people of America, of the world, to figure out what was going on, because it shouldn't do that. But this morning I went in and clicked on the discussion tab on the left, and it pulled up all the discussions for that module, and then I could click on it, and I could create a thread. So we'll see if that works. If that doesn't work, I'll be calling our guru on campus and saying, yo, we got a problem again. But let's talk about cell size for just a minute. Cells, of course, are very small, and there's a reason for that. Must be a reason on that one. Okay, and let's just pretend that we have a cell that is 1 micrometer by 1 micrometer by 1 micrometer. Okay. Now, if I wanted to actually find the surface area, say like for this thing right here, yeah, I would multiply the length times the width, or I guess this would be the length times the width, and that would give me the amount of surface that I have here. Okay, so surface area, I just usually write SA, surface area equals length times width. Okay, so if I wanted to know the surface area of, say, this just one side right here, well, the length of it is going to be 1 micrometer, and the width of it is going to be 1 micrometer, I guess length and width. Anyway, so that's 1 micrometer by 1 micrometer. Okay, so if I multiply 1 times 1, I get 1. A micrometer times a micrometer is a micrometer squared. That's my surface area. Now, if I wanted to know the volume of that box, volume equals length times the width times the height or the depth, whichever. Okay, so my length is going to be 1 micrometer. My width is still 1 micrometer. All of these values are 1. My height is going to be 1 micrometer. So a 1 times a 1 times a 1 is a 1, and a micrometer times a micrometer times a micrometer is a micrometer cubed. All right. Okay, so if I'm doing a ratio of surface area to volume, which is what this thing actually is, the ratio. My surface area to volume is, I have, oh, I didn't do this right, because I have 6 surfaces here. For one surface, it's 1 micrometer squared. But I have the side, the other side, top, the bottom, the front, the back. I have 6 sides, so I have to multiply this times 6. So actually, my answer is 6. 1 times 1 times 6 sides. Side, side, top, bottom, front, back. So it's 6 square micrometers. My volume is just 1 cubic micrometer. So my surface area to volume ratio is 6 to 1. That's your ratio. All right, but what if we double the size of that cell, made it bigger? And let's calculate that. So let's just say it's 2 micrometers by 2 by 2. Okay, surface area, we'll do it correctly this time. We have length times the width times 6 because we have 6 sides. So the length is 2 micrometers. My width, I guess, would be this. It's going to be 2 micrometers. And then I have 6 sides. 2 times 2 is 4 times 6 is 24. A micrometer times a micrometer is a micrometer squared. Okay, now my volume, again, length times the width times the height, 2 times 2 times 2, 2 micrometers, times the other, times 2 again, micrometers. 2 times 2 is 4 times 2 is 8. And micrometer times micrometer times micrometer is micrometers cubed. All right, so surface area to volume, if we're looking at a ratio on this, you're looking at a 24 to 8, or you can reduce that. That becomes 3 to 1. That's significant because here, the amount of surface you have per unit volume, you have more surface, this is your surface area, to volume, the amount of space inside of it. Here, this is the amount of surface that you have to volume. You've reduced your surface area to volume ratio in half, which means per volume on the interior of this, you actually have half the amount of surface for the amount of volume on the interior of it. And I just proved it. I proved it. So what we're saying is if you have a little bitty tiny cell, you actually have more surface area per unit volume than if I have a big cell. Less surface area per volume. Okay, so if I have a cell that's this big and I have less surface area per volume, that's less surface by which you can get oxygen in, carbon dioxide out, nutrients in, and waste out. So the reason cells are small, they're very, very tiny, is because that gives you more surface area to volume ratio. You just proved it. Small cell, larger cell, more surface area to volume, less surface area per unit volume. I mean, you can, there it is, proof. So cells are tiny because all the exchanges that happen across that plasma membrane, the surface, of course, happen right there at the plasma membrane. And so the more plasma membrane surface you have per volume of that cell, the greater exchange you can have. Like I said, the more oxygen you can get in, the more CO2 you can get out, the more nutrients you can get in, the more waste you can get out. It makes the cell much more efficient. So having, you know, and so your problem then becomes, well, if I'm a little bitty tiny cell, then this bigger cell can eat me, right? I can be gobbled up by the bigger cell. So what had to happen during the course of evolution is then, you know, the little bitty cells could be engulfed by the big O cells. Like, okay, I can eat you, you know. So what they started to do then was to create, first, they started to create colonies, groups of cells, and then they started to create what we call multicellular organisms, where you have 70 trillion cells, such as ourselves, you know. So, you know, now we can go out and kill the rabbit and eat it, which I wouldn't at all. I've blown rabbits apart before, and they have like worms all over them. I mean, they are absolutely disgusting. If you've ever like been out on the truck just through a pasture, just going killing rabbits, jackrabbits, and you go look at them, you're like, wait a minute, I'm not touching that. They have worms just crawling everywhere. A lot of worm infestations out there, for sure. My cat has one right now. We have no idea how she got it. And the vet has no idea where this came from or even what it is. They think they have an idea as to what it is. And these people are some of the best cat people, she and her husband, that you could possibly find, actually. They're amazing. With cats. They're cat people. And they do a lot of research, for sure. Anyway, and they're like, I've never seen one of these. And then so they find something in a book that looks almost identical, and they go, and so I'm reading along, and it says, you know, this is an organism that would infest goats and rabbits and blah blah blah. My cat doesn't go outside. This cat will not even go outside. You open the door and she's like, there's a bed in there I want to lay on. You know, she's like, I'm going to be snoozing on that bed. You go on out there. It isn't comfortable. You know, I'm sure there's something could eat me. I'm just going to stay in here. You know, she does not go out. She's never eaten off a plate. She always gets, you know, food, canned food, you know, fancy feast. Basically, that's what she eats, and that's it. So where did she get it? I don't know. It's an enigma. It's weird. I don't like it. My baby's sick and they don't know what to do. One of my babies. I have 3 babies. I adopted another one. Anyway, okay. That's why cells are very, very tiny. Because the surface area, the smaller it is, the amount of surface you have per unit volume increases, because you get greater, and the reason is you get greater exchange. So therefore we have to be multicellular, or something can just come along and eat us up. That just was a logical evolution. Because cells that were very, very tiny, they got eaten up. And the ones that were a little bit bigger created colonies who began to group together. They didn't get eaten up. So over millions and billions of years, what do you end up with? You end up with us. You know, that's what you end up with. It's just logic, pure logic. Biology is pure logic. Believe it or not, it is pure, absolute logic, which is why I love it. Chemistry doesn't seem to be like that to me. Don't tell Miss Jackson. No, she knows. She and I are pretty tight. Anyway, I already talked about this. Yeah, you've got exchange happening at the surface of the membrane. This is basically what that membrane is going to look like. It's a little bit more complicated than that, but I have talked about the fact that 45% of the plasma membrane is your phospholipid. So these are the kind of gray-looking head structures with your 2 fatty acid long tails. And then these, of course, are going to be your proteins. Some proteins move all the way through the membrane. They're called, some of them are called channel proteins. This is a channel protein right here. Channel proteins are used for movement of ions. Like if you have a sodium, you know, or maybe a potassium, or maybe a chlorine, or blah, blah, blah. This goes on. Magnesium, all these ions, they're very, very tiny. So in order to get those into the cell, if you remember these heads, like that head right there, is positive out here and negative here. Well, if you had sodium trying to get in, it's going to hit that and bounce right off. All right. It'll just be repelled. Or chlorine, you know, if you had another one, and it's positive here, negative here, that's these heads right here. So the chlorine would move and would be pushed away by that negative charge. So if you have charged ions, either cations, positive, anions, negative, they're not going to move through this. You got to have some way to do it. So you produce proteins that have channels through them, so we can just move that sodium right on through, not a problem. And it's not just that direction. We can take things out as well. You always have to have exchanges. You know, we're having to make sure our potassium electrolytes, which are basically your elements, your charged elements, ions, you know, potassium, magnesium, and the whole list goes on. But we have to, you know, maintain our electrolyte balance. If your electrolyte balance, you know, is not correct, you're not going to feel very good. And so we've got to keep that moving. And there are people that do have electrolyte imbalances. In fact, that's what causes cystic fibrosis. Horrible. Those people do not typically live beyond the age of 24. I've got a really good friend with cystic fibrosis that I keep up with. And so far, she's doing well, but not doing well, but she's still alive. still with us, that's good. But so channel proteins are for ions. That's what we use them for. And then some of these are not really channel proteins. Some of them are what we would call carrier proteins. I would call this possibly a carrier protein. And we're going to be doing this some more, but while we're here, I thought I'd just throw that in. Carrier proteins, like for example, this thing may have, say, like a notch in it, like that. So if I had something that I wanted to pull to the interior of this cell, say this box thing, it would attach to that receptor. And then there are several ways this can work. One way would be the entire, once they were in the one way, they do different things. But that's what carrier proteins do, basically. And you could go the reverse, too. You could have a receptor in here on a carrier protein, and then, your little box could be in here, and you could flip up to release it. The cell on human cells, for the most part, are basically going to be kind of round. So where's up and where's down? You got receptors all around it. It's a sphere. And I'm sure gravitational pull does have some effect, but there are ways to combat that when you're dealing with cells. And that's not a topic for today anyway. Okay, like I say, that is a simplistic version of the plasma membrane. And there's a smaller version. Okay, we only have 2 cell types on planet Earth. The whole Earth, everywhere on Earth, there are only 2 types of cells, prokaryotic and eukaryotic. The pro means before in Latin. Go. We can stop with that now. So, in Latin it means before. Of course, today we use pro like someone who's very good at golf, or sometimes this light will go out, which tells me we're not recording, so I always have to watch it. They should always be charged, but for some reason they're not. Sometimes go out. Anyway, prokaryotic, the real Latin prefix pro means before, and the suffix, which is carry on, if you put an N instead of a TIC on that, carry on, that means kernel. That's what they first, term they first used to describe the nucleus of a cell. So these are cells that do not have a nucleus. These are just, the only cells that are in this group are bacteria. That's it. They're the simplest cells on the planet. Very simple. They were here at about 3.5 billion years ago. They've been here a long time. How long they've been around? Billion years ago, 3.5. It was only 4.5. So they were here about a billion years after the formation of Earth. It took a billion years to form the first cell. And then these guys, eukaryotic, which we are, they have a true nucleus. EU means true in Latin. Karyon again means kernel, which is basically nucleus. Somebody named it nucleus. Instead of kernel, I probably would have been just fine with kernel. Whatever. True nucleus. So these would be all other cells. And who is that? Well, that would be plant, animal, fungus, protist, like a paramecium. Okay, so that's all the other cells on the planet. And these appeared at about 1.3 billion years ago. So these are kind of the new kids on the block. And Once they developed a method of sexual reproduction, which we'll talk quite a bit about when we finally get to that, and that's pretty much a semester, it really speeds up the process of evolution. And I can explain how that works, but it's just like, whoa, all of a sudden things can just evolve like, on a day-to-day basis. It's possible. It is possible. So it is crazy as to how fast organisms evolve with that sexual reproduction. Very interesting. Anyway, those are the only two cell types. And we'll look at prokaryotes and eukaryotes in lab. Now, this is a prokaryotic cell, a bacterium. This one has everything you could possibly put on a bacterium. They don't all have all these things. This is like, if it had everything possible, this is it. Well, no. Most of them are not nearly this complex. Okay, so let's begin with the DNA. The area where the DNA is located is called the nucleoid, and that is all it is, which I find to be really weird. It is an area with DNA, or, you can call it a chromosome. They do now with chromosome. All right. And there is only one chromosome. One circular chromosome. So really, it has a beginning, and that never has an end. It's circular. It's all connected. Now, ours will have 3 ends on them. These don't. Now, that looks like a pile of spaghetti there, but if you were to take it all out, and you just have one continuous loop as a chromosome. So all living organisms have to have some sort of DNA. The nucleoid is just wherever the chromosome is located. So if that chromosome, that pile of spaghetti, were to move over here, that area would be called the nucleoid. So if it moves over here, that area is called the nucleoid. But if it's sitting right here, that area is called the nucleoid. So to me, that's one term in biology that I find totally, completely useless. It's wherever the DNA is floating around. That's the nucleoid. People confuse it because in a nucleus, and within the nucleus you have a nucleolus, but then in a prokaryotic cell you have a nucleoid. Weird. So let's confuse all the students we possibly can by throwing in a term which means wherever the DNA is floating. We'll call that the nucleoid. The significance is, if somebody could explain that to me, love to know. Never heard it. Wherever the DNA floats. I would love to meet the person who came up with the term. What's the point? You're used every freshman biology student going through biology, and I'm not going to thank you for that. The fimbriae, well, let's work our way out. Here are the, of course, here's your chromosome. Then you have these little bitty dots. Those are our ribosomes. Now, these are smaller ribosomes than what we have in eukaryotic cells, or what are called 70S. That S is basically a spin rate, and I'm not going to get into much detail on that, but they're small ribosomes is what that really amounts to. They're different than what we have in our cells, just different ribosomes, very small. That's where proteins are produced, so site of protein synthesis. So that's where we produce proteins there. And we'll talk about that also in lab. Okay, and other than that, you do have a fluid in here, which I don't see that they've listed, but the fluid is a cytosol. Cytosol, that means cytoplasmic solution. Now, if you say cytoplasm, That's different. Cytoplasm equals the cytosol plus any organelle that you have. Well, really the only organelle we have here is a ribosome. The DNA is not an organelle. So cytoplasm is cytosol plus organelle. I think I spelled that right. So the fluid is the cytoplasmic solution, cytosol. Cytoplasm includes whatever is floating around in it, and that it would be an organelle. The genetic material is not an organelle. Although, if it's got a membrane around it, you call it a nucleus, then it's an organelle. Again, go figure. They do really particular things, very significant, very specific, things in biology that just make the difference between you pass the MCAT or you don't pass the MCAT. It's like, you got to pay attention. you have to. It's like, what? Are you kidding me? So this is not an organelle, but if I put a membrane around it, then it is. We'll call it a nucleus. Well, they don't have nuclei in a bacterium. So, and some books will tell you the nucleus is not an organelle. So then you get into all of that. It's kind of bizarre. All right. So bacterial chromosome is just one circular chromosome. Okay, now we'll work our way to the exterior. The plasma membrane would actually be, although they didn't do it right, plasma membrane would be this thing right there. Okay, that's the plasma membrane. It lines the cytosol, so the fluid on the inside. It lines that, and that's where the exchanges occur. The cell wall, which would be this thing right there, kind of an orange. The cell wall is a rigid structure that does give the cell some shape. And not all bacteria are rod-shaped. That's just one type. And then the capsule, I'll put a plus or minus beside that. And what that means is some bacteria have these and some bacteria don't. Now, if it's compact, dense, you would call it a capsule. So this is dense. If it's not very dense, you call it the slime layer. So there's a difference. Not dense. Okay. The flagellum obviously is used for motility, for movement, and I'll put a little plus and I'll put a big, huge minus. Most bacteria don't have flagella. They don't swim. They don't walk. They just lay there. Life of a bacterium. It just lays there. They're not very active. They just lie around and absorb food and divide, and they might produce some things, toxins or something. Basically, that's it. That's an exciting bacterium too. That's the really exciting ones. All right. So we're on slide 18, where we'll pick up tomorrow. So we begin the animal cell tomorrow.